Hello, everybody, and welcome to the G2M Research webinar on computational storage versus virtualized computation and storage in the data center. My name is Mike Human. I'll be the MC for this. We have a great panel of people from ScaleFlux, PlyOps, and Acronics. Let's give everybody a minute or two to join, and we'll go ahead and get started. Hello, everybody. This is Mike Human. I'm the General Manager and Principal Analyst at G2M Research. Welcome to our webinar today on computational storage versus virtualized computation and storage in the data center. We'll have presentations from some industry experts on the topic. Before we go into that, let me kind of walk you through some of the introduction of the topic and the ground rules. So our webinar will last about an hour, maybe slightly over an hour. Each of the panelists, and we have three of them, will be providing a 10-minute presentation on their view of the topic, and then we'll go into three panel questions that we'll ask. We'll also have two audience surveys that you'll get to answer, and we'll also have a Q&A, audience Q&A session at the end before we wrap up. A couple of things: when you submit your Q&A questions, please use the Zoom Q&A window. We'll put in questions whenever you want, and then we'll go ahead and answer them at the end. Also, this session is being recorded. We'll make that recording available to everybody who registered for the webinar. On Thursday, you should also get a PDF of the slide set along with the link to the recording so that you can go ahead and see what's going on and what everybody said. Finally, just don't feel shy to ask any questions. All questions are good questions. And so with that, let's go ahead and get started. So what is computational storage? And if you look at what the Storage Networking Industry Association, or SNIA, defines it as, they say computational storage is a set of architectures that provide computational storage functions coupled to storage, or you could say processing functions. And the whole idea is offloading host processing to reduce data movement within the server architecture and across the network. These architectures usually improve performance because you are actually getting rid of the movement of that data, which can take a long time for very large data sets. And it also enables parallel computation. If you have multiple storage devices that have compute, memory, storage, and I/O in them, you can do it in multiple places. So you can easily scale performance just by adding computational storage devices. So if you kind of think of it in that way, it's really what computational storage comes to. It's really how do we take functions that occur in the CPU today and move them into a variety of new devices. It's kind of like offloads in the network world or in the security world. It's the same idea, right? And SNIA defines three different types of devices. You have computational storage devices, or CSDs. And those are actually storage devices. Think of an SSD or something like that also has computational capabilities built into it. You also have computational storage arrays, or CSAs. And a CSA is a storage system that also has computational storage in it. So rather than being a single device, it could be a bunch of devices in a shelf. It could be a huge rack level system that has both processing and storage, or anything in between. And the third concept is computational processors, or CSPs. And the idea with all of these is how do we get stuff off the CPU to devices that are in the storage domain so we can avoid moving data. And it's kind of like Apache Hadoop, but at the micro level as opposed to the data center level. Hadoop MapReduce really says, instead of moving data over to where the computation is, let's use the computation where the data exists. And this is exactly that same concept. Some of the challenges to computational storage that we've seen over the past several years as it's been introduced: application modification. Some computational storage approaches require you to modify your applications. That's not as hard if it's open source. It's a little harder if it's proprietary applications like SAP HANA or things like that. That can increase the adoption time. So that's one issue that we'll talk a little bit about. Go-to-market channel adoption. Obviously, most people are buying data center equipment and the enterprise are buying it from a handful of vendors or IT sources, whether they're OEMs, resellers, or SIs. Most people don't want to integrate themselves, so that can be a hurdle as well, and we'll talk a little bit about that. Crossing the chasm is another one. One of the questions you always get from the IT people, and them being a fairly conservative group, is who else in my space is using this? What other companies like me are using this, and what was their experience? So it's kind of a chicken and egg problem, and we'll talk a little bit of that. And then standardization. This is actually one that I think computational storage is doing well in. SNIA has done a lot to standardize that and to avoid vendor lock-in, so that's a good thing. Let me introduce our panelists now. Our first panelist will be Tom Spencer. Tom's a Senior Product Marketing Manager at Acronix. We also have with us Tony Afshari from Plyops. He's the Senior Director of Product Line Management. And JB Baker, the VP of Marketing at ScaleFlux. All three big names in the computational storage space. And again, I'm Mike Hume. I'm the Principal Analyst at G2M Research. And with that, let's go ahead and introduce Tom. Tom, go ahead and take it away.
All right, thanks a lot, Mike. Let's go ahead and hit the first slide. So everybody knows that worldwide, there's a big data explosion, and I'm not going to get into all the details behind that, but what I thought would be interesting would put out a few statistics. By 2025, they're expecting to have 30+ billion IoT connections and up to, or if not surpassing, 175 zettabytes of worldwide data, which is a massive amount of data. To keep the presentation short, I didn't put a slide in on edge computing, but edge computing is another factor. So a lot of applications are moving out of the core data center, moving out to the edge. A lot of that's driven by not wanting to move data over the network, but also a lot of latency sensitive applications. And so anytime you have to move data, as Mike was pointing out, over a network, whether it's at the edge or in the core, that's going to be latency, that's going to cost money, that's going to be a lot of power. We want to compute this where the data is, hence computational storage. If you look at how the data can move quickly, 5G versus 4G, look at some of these stats: 100 times faster than 4G, 250 times higher density, 100 times lower latency. They're talking single-digit millisecond latency numbers. Next slide, please. So in the core data center, if you go back a number of years, data accelerators started getting introduced when workloads were increasing, when data was increasing, they would throw more servers at the problem. Now, this starts to cost a lot of money when you're talking about 300 and 400 watt CPUs, servers being costly anywhere from several $1,000s to $10,000. So data accelerators entered in. A lot of these early on for AI and ML use cases were GPUs, but there's a whole market now for GPUs, ASICs, and FPGAs. And at the end of the day, these data accelerators are reducing latency, they're reducing power and cost, they're reducing the real estate footprint, and they're also increasing the performance. So what we're seeing now with data accelerators is they're not only being used inside the core data center, they're actually going all the way out to the edge. And they're getting integrated into computational storage. So if we look at some of the computational storage use cases, the data can actually come in over the PCI Express host interface, or it can come over the network with, say, for example, NVMe OF. Some of the applications in computational storage could be AI/ML, in-memory database applications. Big memory is a new technology that's getting a lot of traction right now. Also look at video. You've got transcoding, you've got encode, decode. A lot of these things can be done at the storage. If you go beyond that, you've got erasure coding and compression, and then ultimately you've got encryption. Now, I lump all these together, and how does this tie back to data accelerators? You've got a new market, computational storage, and changing of the architecture of the networks. There are going to be a lot of moving parts. There's going to be new standards. There's going to be different workloads. There's going to be install once and reuse many times. And if you look at all these blocks, you're going to want to have flexibility. And that's where a lot of these data accelerators come in. They're flexible platforms. They're programmable. You can put them out in the field, and then you can repurpose them. FPGA data accelerators, some of the benefits there, you get ASIC-like performance in terms of speed and latency, and you still get all the flexibility of, say, a CPU, a GPU, or an IPU. Let's go ahead and hit the next slide. So if we look at some of the challenges that Mike had noted at the beginning of the presentation, so application modifications, as I noted, a lot of these applications are going to change. They're going to change because of standards. They're going to change because of workload or requirements. So you're going to want to deploy it once and repurpose it. As far as the go-to-market channel adoption, by giving that flexibility, there's going to be less risk in terms of adopting the technology, putting it out into the infrastructure, because of the flexibility, you'll be able to shape it into whatever use case you need. As far as crossing the chasm, all of that mitigation in terms of risk, the ability to have that flexibility, the ability to change is going to put some IT managers at ease. And same thing with standardization. As we develop new standards, as the standard moves, we move with it. You've got the flexibility built in. So the FPGA data accelerator, again, ASIC-like performance, but the flexibility of a CPU, GPU, or IPU. Next slide. So Achronix is a high-end FPGA company. We compete with the likes of Xilinx and Intel. And you can see on this slide here, we've got the Speedster 7T family. This is FPGA chips. I won't list through all the specs, but we have the highest bandwidth FPGA in the market with 400 gigabit Ethernet, PCI Express Gen 5. We've got a technology on chip that we call a two-dimensional network on chip. And that is a hardened piece of IP that moves data at 10x the speed of our nearest competitor. And that allows users to use the FPGA logic that's on the chip, the LUTs that are on the chip, but still be able to move the data faster than the data is coming into the chip or going out of the chip. So it prevents bottlenecks. We also have integrated machine learning processors. These are optimized DSP engines, very flexible. So you can run different algorithms on the devices. Covers INT, floating point, block floating point, number formats. Now, one thing that our company does that none of the other FPGA guys do is we offer embedded FPGA or IP. So now you can take the FPGA technology and you can integrate it into ASICs or system on chip solutions. What that allows someone to do, if you look at the cost of developing a 7 nanometer ASIC these days, you could be looking as little as 20, 25 million. You could be looking as high as $100 million investment. By putting flexible logic on the chip, that allows you to have a longer product life, faster time to market. You build that flexibility into a lot of these use cases where users want to have different workloads, different AI or ML network solutions. So you get that flexibility. And then finally, we have data accelerator cards where we take our FPGA chips. In this case, we've got the Bitware platform. This was a co-development between Achronix and Bitware, where we took our AC7T 1500 FPGA, put it on the card, and now you can take that card and go build various applications with it. Next slide. So wrapping all this up, the data is growing exponentially, 175 zettabytes by 2025, 30 billion IoT devices out in the market. And data accelerators are a key component to every network out there, whether you're in the core, whether you're at the edge, whether you're in your computational storage device. FPGA data accelerators, excuse me, provide the programmability of a CPU, GPU, or IPU, but they run very similarly to an ASIC in terms of speed and latency. The FPGA data accelerators will help you bridge for market adoption, market acceptance in new technology, changing specifications, varying workloads. And Achronix is the only high-end FPGA company that offers discrete FPGAs, embedded FPGA IP, and data accelerator cards. So if you want to get started with Achronix, you can follow this link. You'll register online. We have evaluation licenses where you can try out our tools. Reach out to Achronix, let us know how we can help you in your program.
Thank you much, Tom. And just emphasizing or amplifying one of the things Tom said, it reminded me as he is on his first slide of a statistic I saw that was basically 34% of all power consumed in the data center is used moving data. So that's yet another reason why this is a big issue for data centers and for other people. And with that, let me introduce Tony Afshari. Tony is a Senior Director of Product Line Management and PlyOps. Tony, you should have control of the screen now.
Excellent. Thank you so much. Let me see if I can move my... Great. There we go. Okay. Thanks again for the introduction. My name is Tony Afshari. At PlyOps, our mission is to massively accelerate performance and dramatically lower infrastructure costs for flash-based data-intensive applications. These include databases, analytics, AI, ML, and exacerbated with 5G devices and IoT. What we are really proud of is the capability and the core engineering know-how that we have. We have experts in database, flash storage, and semiconductors coming from many industries, many familiar names, including Samsung, Intel, Kioxia, Yahoo, Amazon, etc. We're very proud of our team. We are working with 20 Fortune 500 cloud and enterprise companies. And some of our great investors include SoftBank, Intel Capital, NVIDIA, Western Digital, and Xilinx. We are getting a lot of accolade out there, including being a top 10 cool tech company from CRN. I invite you to monitor plyops.com. We have amazing news coming in the next few weeks and lots of new accolades coming our way. So keep an eye on plyops.com. Just to resonate some of the things that my colleague mentioned, but also maybe focus a little bit more around what's happened with where SSDs are going and where the CPU capabilities are. The curve on the left shows essentially where SSDs are going from, where they were in the early days with being bottlenecked essentially with the interface itself, let's say SAS or SATA, and then with the invention and the coming of NVMe SSDs, you had almost like a floodgate that you opened, because now all of a sudden you had devices that were extremely faster, extremely more capable, much denser. And now you're exposed to the shortcomings that CPU has, because CPU essentially is taking the opposite direction from where NVMe and NVMe SSDs are going. So you could compensate for this by using more CPUs and more cores and more servers, but this doesn't scale because this is very costly. To deep dive in this a little bit, let me show you another picture, and that is today or yesterday, and reflect some of the things that I said previously. We were in sort of a compute-centric era, or I should say CPU-centric era, where the CPU was doing pretty much everything, running traffic controls and doing its most important job, which is running the applications, but also storage management. Well, if you're running storage management and you're dealing with slower devices, let's say slower SSDs or even the mix of HDDs, well, what you're doing and the loading of that on the application is good, because generally those devices tend to be slower. But as these devices and this storage is getting better and faster, and more applications are going to all flash because they need those fast responses from transactional type IOs that go back and forth to the SSD. Well, now you're seeing the exposure of the shortcomings of how the CPU is running the storage management. So today's data is a data-centric approach. And by the way, this problem is getting worse because now you have more devices on the edge. You have more devices on the 5G network. So the amount of data that is hidden in the data center is just continuously growing. We've seen a good trend here. We've seen how AI and ML applications have been offloaded and moved to unique hardware, started with GPU, but more and more is becoming very focused around exactly what AI and ML needed. So this is not a new way of, to do. So GPU and AI ML started that, but you're seeing the same thing with storage. So storage management tasks are moving to dedicated data processors. And this follows the computational storage model. And this allows the CPU again to focus on what it does best. You know, let's use those cycles, those expensive cycles, for using to run the applications and serve the applications. In some models, we even show the traffic control getting offloaded to a DPU. And so more and more, this is around what's the right thing to do around data. Once storage tasks and storage management is in our domain, well, we apply what we know what to do with it, make the data run faster, provide faster data to the application so that the application runs faster, provide better capacity, higher capacity, more reliable capacity, and improve the endurance of flash so that you can get more out of it. You can fill up the SSDs more. You can use lower cost SSDs and flash types. So what is it that we do? What is it that PlyOps does? We are a half height, half length PCIe card that can easily fit in any server. And at the core of it, we are the PlyOps storage processor seamlessly manages data flow from application to storage. We shape the data for optimal placement on the lowest cost SSDs, and we enable very high performance with fully offloaded data protection and inline transparent compression. Well, out of this translates to the pillars that we stand on. Reliability, and that's being able to provide drive fail protection at the node level that is twice as fast as RAID 0, which is the fastest striping capability and what most data centers are using today. Be able to show 2 to 15x performance improvement, depending on the application that is running on the cloud server. Be able to present up to 6 times more capacity to the user, and be able to make more efficient, whether it's TLC, QLC, or ZNS for any workload. So economizing these lower cost and great flash technologies for all workloads, and taking the guessing out and allowing the cloud operators to just be able to load and host any application, any workload on this wonderful, economical, reliable infrastructure. A little bit more about how we get placed in the system. We require no change to the applications, whether it's an application server running popular databases, or even a storage system, disaggregated storage system with distributed file systems. We essentially are another NVMe block driver, and in the system, the host will require and the application will require no change. We do have a transparent agent that runs in the background. We manage the writes and reads that go in and out of the application. We can directly read from the SSDs, or we can read the SSDs into our domain and pass them on to the host. And we do this, we can manage the storage adjacent to us, and that allows for any kind of an SSD, any kind of flash to sit there. It could be a QLC SSD, it could be a TLC, it could be Optane. It's a mix. And that storage, those storage blocks, that adjacent storage doesn't need to sit in the server. It can be sitting outside in the rack through an NVMe over fabric type connection, or even KB over network. So two types of usage case that we see out there is, and where people are using devices like ours, is one with disaggregating infrastructure. So the way traditional storage worked in traditional enterprise IT worked is you had your islands of compute application servers, and you had your storage arrays sitting somewhere else. And it's very nice to be able to scale those, manage those, isolate those. But that's not how hyperscale or the cloud infrastructure started. Everything was combined in one, and the unit of compute, storage, networking was the server. But more and more people are trying to apply that model, but still use the same essential building block, which is a server. Now, servers can be grouped together to create storage pools. Let's say with a storage file system, with a distributed file system, something like Gluster or similar type solutions. And that way, you're still using commodity servers, you're still using open source software. And what you can do is scale those two separately. You can isolate those two separately because of security reasons and etc. Especially nowadays with the realities we're seeing with ransomware and etc. And with those storage servers, people are using devices like FlyOps to be able to make those denser, make those more reliable, make those more economical, and then make them run faster. Same thing goes with people that are focusing on making an all-flash application server essentially better. So people are putting in the FlyOps in servers that are dedicated to run, certain application servers, the ones that require and rely on the power of flash, the latency that flash brings into the picture, to be able to speed up the transactions that go back and forth to that SSD. And so examples are MariaDB, Redis, and Mongo. I wanted to bring up, okay, so what does this mean? What's the economic and advantage cost of this? Well, let's take the first case, for example. In this case, we have a Gluster server. It's a 10+2, let's say, or something similar to that. It is a nice way of being able to have majority of the things that, let's say, a very, very extensive all-flash array brings in a traditional IT model, but it's in the hyperscale case. And so the building block still is open source software, commodity servers, none of that changes. But the nice thing is that you have all the things that, all the resiliency essentially that you have from the traditional model. Well, there's some limitations with it. Is you can only make these nodes density to certain capacity, because eventually you'll have the problem with rebuild. Even in the case a server goes out, and you have the problem with not being able to manage the failure domain getting too big. And so what the customers are doing is they are now creating groups of SSDs behind a PlyOps data accelerator, and we are applying our principles of providing inline compression and being able to condition the data or shape the data to a point where it's very, very optimal to be written to flash. And then at that time, when data is already conditioned, then being able to apply a data protection algorithm to it is a very nice thing and simple thing to do. And we have designed an algorithm that is, again, written for flash, so it's brand new. It's not something that, you know, has a lot of legacy associated with it. It's designed for flash. It doesn't need to worry about HDDs, and so makes the performance really, really fast. So this group of SSDs here that are data protected and accelerated with PlyOps are also very, very dense, because instead of TLC technology, we're seeing QLC technology. So we are essentially doubling the capacity per each brick of cluster. And so what does that mean? Ultimately, this allows the customer to massively increase the capacity. We went from 3.2 petabytes per this cluster to 4.3 petabytes at lower cost, at higher performance. So all of that essentially translates to a 40% savings in cost, 100% reliability, because now we can recover from a single drive fail without taking the whole node down, and then be able to provide the same endurance and performance as TLC drives. Another example is when we talked about that application server. In this case, the way the customer will benefit is how many instances of a database, let's say MariaDB or MySQL, they can host, and their unit of compute, which is a single server with 2 SSDs, each 15 terabyte, running RAID 0. Well, what we're doing is consolidate this picture on the left into a single server. So we went from the cost of 3 servers to a single server, and was able to put much denser storage in that server, so that you can afford to put the same instances. In this case, they're even putting more instances of the databases. So they went from 15 to 20, and the total capacity went from 41 terabyte to 66 terabyte, and the reliability improved significantly, because they had, with RAID 0, you get great performance, but you have the problem of node failure, and the node failure reliability went from 600 failures per year to 0. So again, we are a device that run this incredible algorithm. It happens to be running on our own dedicated hardware and our own gates. It's a version of the computational storage, but you know, somebody could run all our algorithms on Xeon cores. It would have taken 1,000 Xeon cores to run the same thing. So the fact that we can do it in RTL, we can do it completely offload the CPU from these tasks, gives us the ability to provide very high reliable, very high performing, higher capacity, and more efficient storage.
Thank you, Tony. That was great. Let me see here. And with that, let me introduce JB Baker. JB is the VP of Marketing at ScaleFlux. JP, let me pass you control real quick. You should have control, and go ahead and take it on.
Okay, thanks, Mike. Yeah, it's in a way it's good to go last because Tony and Tom have done a great job of highlighting some of the problems and the scope of the size, the amount of data that's getting moved around, and the bottlenecks that we see out there. My screen does not want to go forward. There it goes. Okay. Yeah, it suddenly caught up.
Yeah, there's usually a lag the first time you move it.
All right, I'm gonna wait. Hopefully it'll stay on the slide. Nope. I think that.
This is why we don't want to move data over a network, right?
Yeah. Process it locally.
There you go.
This lag time, the latency issues, that's a big part of the problem that we solve. So I'm going to give you a quick, what is ScaleFlex, what's our product, then going to highlight the problem, a little bit of a nuance versus what the other guys have said, and then the benefits that we see. So ScaleFlex is a leader in computational storage. Our products, we focus on the computational storage drives. Company was founded in 2014. We were the first into production with a computational storage drive back in 2018, and we launched our second gen last year, the CSD 2000 that you see pictured here. It's really great because you can just plug this into any industry standard slot. We have the U.2 and the low profile add-in card options to turn those PCIe slots into drive bays as well. The company has manufacturing both US and China, big patent portfolio, well-funded startup. I just closed another round last year, and we're in production. We're shipping to hyperscale, web scale, and enterprise customers worldwide. We've continued to get recognition over the years since we started launching the product. A couple of awards back in 2018, a couple more last year, and then just in the last couple of months, noted by Data Breakthrough Awards as Flash Solution of the Year, and mentioned or brought as one of the 4 vendors in Gartner's Cool Vendors in Storage and Hybrid Infrastructure. All right, now it's building for me. All right, so what is a computational storage drive? Mike gave you the definition earlier, but from our perspective, it's very simple. It's, this is not a, you have to be worried about the integration and worried about how complex this is to use. Very simply, it's an enterprise PCIe SSD plus added functionality. So our product, we're using, like I said, the standard form factors, standard capacities, 4, 8, 16 terabytes, TLC and QLC options, and then all the expected features you'd have from an enterprise drive with power loss, data protection, ECC, LDPC correction, et cetera. And then what we add into this, in this generation of product, is the transparent compression and decompression. So you're getting that functionality, offloading it from the host to get the cost advantages of compressing your data and storing compressed data. And then beyond that, we allow you to do the extended capacity. So take the 4 terabyte drive, you can use that to store 8, 12, 16 terabytes of data. We allow you to configure the over provisioning. So instead of having to buy a 3.2 and then a 3.84 terabyte drive for different use cases, we sell you a 4 terabyte drive, you set the OP to where you want. And then we also do support atomic writes, which has significant benefits for database applications like MySQL and MariaDB that use a double write buffer to assure that there's no torn pages in the event of a system power loss. The atomic writes gets rid of that and helps extend the endurance and improve performance in those applications as well. All right, so Tony had a very similar diagram here in the same terminology, where traditionally we've had this processor-driven architecture where all the data had to push through the CPU, and that created bottlenecks at the CPU and on the host memory bus as well. We've seen accelerators come in on the side, but there's a limited number of slots there to put these accelerators and FPGAs, and you still have all this massive data movement down to the drives. And I fully agree with the diagram that Tony showed of the problem really didn't exist a few years ago because the storage was too slow. The CPUs were significantly faster. They were growing faster than the storage IO and the network IO. And over the past few years, we've had that transition from hard drive to SATA to SAS to NVMe SSDs, and then to the Gen 2, Gen 3, now Gen 4 PCIe SSDs. And that those are just far outstripping the pace of performance growth in the CPU and DRAM. And the same thing on the network side with the shift to higher and higher speeds there. So this has created this bottleneck at the CPU and created the need for us to transition to a data-driven architecture to get rid of these scaling challenges and bottlenecks. So what we see with the data-driven architecture is pushing some of those functions down to the computational storage drives or with computational storage processors as well. At ScaleFlux, what we're doing is integrating some of the functionality right into the drive. These different icons are just there as you can do different functionality in there over time. And what we see with putting these compute functions down in the drive is now we have a very balanced compute and storage I/O infrastructure. We're able to put many compute engines in, and the performance of those is going to scale very cleanly as you're adding data storage capacity. So because every drive is going to include a optimally sized performance of that compute engine. So it allows you for a very, very parallel computing infrastructure and simplifies the scaling. And then what we've seen in real world for benefits with our customers from utilizing the CSD 2000, the currently shipping product, really around the performance and cost and capacity, which also translates then into the density of how much storage you can put per node and reduce the number of nodes you need to reduce that data center footprint as well. These are just some example applications. The features definitely apply to additional applications. These are just some of the key ones that customers have already been deploying. And what I've highlighted here in the bold italic is the key thing that the customer was looking for. So with Aerospike, they are very, very, very focused on latency. They need that super low, consistent latency, and we reduce the number of outliers by 98% versus the next best drive. In MySQL MariaDB, what we hear from customers there is more about, hey, look, performance is great and we'd like to reduce performance, but the bigger thing for me is I want to reduce my cost, the cost to store all of this data. And by compressing the data and expanding the effective capacity that you're getting per gigabyte of NAND, we're massively reducing their storage costs without incurring any performance penalties. So that's the big thing. They weren't looking necessarily to go 10x on performance, but they definitely didn't want to go any worse on performance by implementing compression. Similar story for Postgres. And then on Redis, what we've seen is when you're doing Redis on Flash, you can have, there's a heavy write workload in this application, and that can burn out SSDs relatively quickly and prevent you from using those low cost, low OP, TLC, or even QLC drives. And by utilizing computational storage, we're able to massively improve the endurance of those drives and help align the lifespan of the drive with the lifespan of the server, and allow for the use of those lower cost SSDs as well. So that's kind of it in a nutshell. We've got a lot more data on our website, scaleflux.com. So definitely come and visit. We've got quick videos on some of the different applications and performance benefits as well.
Thank you much, JB. That was an outstanding presentation. Let me answer one Q&A question we have real quickly. And the question was from Caustic Energy, and the question is, hi, who can we reach out to ask for recording this webinar? Everybody that has registered for the webinar will get a link to the recording. You should expect that to come out on Thursday. So that's when you should see that. You'll also get a place where you can download a PDF of the slide set. So with that, let's go to the panel question and answers. So we'll start with question number one. And on this one, we'll start with Tom, then we'll go to Tony, and then JB, and we'll just kind of rotate it around as we go through. So the question is, flash storage devices seem to be going in at least two different directions. You got hyperscalers asking for devices that they can control at the micro level. Think about open channel or things like that, where they really want to get down and really control everything that happens in the SSD, including garbage compaction and everything else. And then on the other hand, data center devices are adding more and more intelligence. And in some cases, I'm thinking of the Kioxia device specifically, network interfaces. How do these two trends impact the positioning of computational storage in the data center? We'll start with Tom on this.
All right, thanks, Mike. So if you look at the top hyperscalers, these guys are developing their own technology all the way down from silicon, subsystems, servers, appliances, and software. And if you look at the complete opposite side of that, go to enterprise. There are some enterprise data centers where they're developing some of their own technology, but you have this very disparate set of requirements from the high-end hyperscalers all the way to enterprise data centers and everything in between. And so you've got that disparity. And then on top of that, you have the infancy of computational storage, and then you have changing workloads and so on and so forth. So all of that comes back to when you want to take a new technology, and computational storage is a big step forward on cost reduction and big increases in performance. As long as that flexibility is built into those devices, that's going to take the technology of computational storage on a faster track to adoption across the market. And so all these data accelerators that I talked about are a path to that. And FPGA technology is one of the key technologies for enabling that capability.
Excellent. Tony, what do you guys at PlyOps see on this? What are your thoughts?
Sure. By the way, this is a great question. Let's talk about open channel itself. I really didn't take off, but another great example for this or similar thing would be ZNS, which is now emerging as a new standard to accomplish essentially the similar goal, which is minimize SSD costs and the cost of the writes. I mean, ultimately, given where we are with the economy of pandemic recovery, everything being shortage, nobody wants to do extra work. So if this work is being done and if it's available from a vendor, the biggest hyperscalers in the world will take it. So another example of this is QLC, which is even more relevant ahead of ZNS, and it's very sensitive to writes on performance and endurance. So if you're managing all this, if you're the operator in a cloud or in a data center, it requires a lot of careful data shaping and deep understanding of flash, where to write it, how to get the high performance. All of this is not trivial. I mean, it requires a lot of specialized systems, and ultimately it will tax the CPU to do all this stuff on the CPU. So the easiest is to allow dedicated data processors to do this work, and hyperscalers are very open to this because they know this is not an easy task for them to do. And so computational storage devices like PlyOps be offered to manage all this data shaping and placement, to use the lowest cost flash like QLC, and then better performance and endurance, provide better endurance that what software can do.
Excellent. JV, what do you think on here?
I think Tony read my notes. Yeah, I mean, really, the same thing. I mean, open channel didn't fully take off. There's still some pull for it, and now ZNS is coming in as an alternative to help address those problems of how do I get more value for my flash storage dollar, right? Addressing some of the challenges with the endurance, particularly as you go to QLC, getting to be able to use more of the NAND and lower the over provisioning. So, you know, those challenges are, computational storage goes after those as well. So, I mean, I really view it from the CSD perspective as by adding that functionality down into the drives, we effectively solve those same problems that they were going after. And we do enable those major customers some of that micro level control, maybe not to the extent that a full open channel would have allowed, but you know, we're allowing for programmable resources down in the drives so they can push their specific functions down into the drive or down into the computational storage processors. So I really think that the computational storage is just the evolution of getting to a manner of solving this problem in a more industry standard, more adoptable way.
I like that. That's a good answer. Okay, with that, let's go to audience survey question number 1. And this question is, how does your organization view the positioning of computational storage in the data center versus conventional storage, computation, virtualization architectures? In other words, how do you see it versus the way we do things today? This is a check 1. Let me go ahead and launch that poll, and I'll give everybody a couple minutes to fill it out. And while you fill it out in the Zoom poll window, we will go ahead and move on to the second question. And the second panel question is, one set of use cases where computational storage provides value add is an extremely large data sets. Think about petabyte scale type of problems, where it eliminates the need to move that data across the PCIe bus, or even worse yet, across the network, right? How common are these types of computational problems, and how does computational storage compare to other alternatives for solving these problems? We'll start with Tony, then go to JB, and then to Tom.
Right. Again, another great question. And I think one example that I like to bring up is when you're doing reliability and let's say some kind of erasure coding on the data. And the bigger that data is, the number of trips you have to take back and forth to the drive, to the host, to the CPU, it gets massive. So that's a problem. That's one reason, on top of the slowness and resource and the cost, that people are not putting those kinds of solutions in hyperscale and web scale type ideas. But again, if offloading this to a product like Pliops that combines compression and data shaping and dry fill protection will allow this to be done significantly faster. Think about it, once data is compressed and turned into variable size objects, then it's always written sequentially and on the boundaries of flash logic. So essentially you're writing the data just once. And if you're doing it like that, then adding erasure coding on top of that becomes very effective. There is no read modified write. There's no extra trips going back and forth to the drive. So this allows for data protection to be faster than RAID 0, even during rebuild. And it will enable customers to build denser nodes that can put more demand on them while they're improving their SLA.
JB, what do you think on this one?
Yeah, well, first on the scope of the problem, it's not just moving data across the PCIe bus, but also to the host memory and across the network. So there's, each one of those can become a bottleneck in a given deployment. And while, the petabyte scale problems, they're absolutely out there. I mean, think of like autonomous driving and some of these exploration things, like the model you might see from NVIDIA on the Mars lander, and all the data that's being crushed to create those models. I think those are not as common necessarily as smaller scale problems, but when you consider some of these smaller scale problems in aggregate, they do become more petascale. And what I mean by that is, like, you may have many queries from multiple compute nodes pinging the same disaggregated storage nodes. So now while maybe you're only working with terabytes of the data set, you're turning it into petabytes because you're trying to access it so many different times. Or you're in a cloud environment where you've got multiple of these terabyte data sets that in aggregate, you're now creating this petabyte scale problem of transferring data. So, I kind of take it beyond just, do I have a petabyte of data for my problem, to, am I trying to move petabytes of data to solve multiple problems? And I think that is extremely common. Now, how does computational storage help with that, or how does it compare to other solutions? I think computational storage is extremely effective at reducing that data movement and scaling its capacity to provide the storage or the computational functions with the data set size, because we're bringing that compute function right down close to the media, right? So you've had to move it off of the flash into the SSD controller, or potentially one more step out to the CSP, as opposed to having to move it out multiple steps up to the CPU or to a smart NIC or something to do that function. Now, you know, while we're focused on the CSD and reducing the data right where the data lives, there are tiers to this. So we can't do everything in the CSD. We're going to do a lot of stuff in the CSD, but then we can reduce how much data has to get moved off of the drive across PCIe up to the system. But then CSPs and smart NICs can do additional functionality that's going to help reduce that data movement across the network or into the CPU and DRAM as well. So I don't see this as a one solution fits everything. This is a these are co-opetition. They're both complementers and competitors in this space.
No, good, very good point. I think the number of data movements, you know, has as big of an impact on latency as you know how much data you have moving. So reducing that certainly is value as well. Tom, what do you think on this one?
Well, one of the things that JB pointed out that I certainly was going to speak to is, you know, this isn't limited to a PCI Express bus, right? It's over a network, it's over a PCI Express bus. When you talk about networking, you're talking about multiple writes to memory just to get data to and from storage. Then you got to move it back again to the CPU to do work on the data. So all of those things introduce latency and power and cost and so on and so forth. In terms of saying that the use cases are driving the need to reduce the number of times that we move across these different buses, you know, go back to the data that we're talking about, going all the way up to 175 zettabytes by 2025. And what are these use cases? So the smartphones and all the streaming technology, the smart cars, we do a lot of programs with autonomous vehicles and ADAS, and looking at the latencies involved and the amount of data that has to be crunched. A lot of that needs to be done real time. It's got very low latency requirements, and having computational storage as part of that solution, it just simply makes sense. The less amount of times you need to go across a bus or a network, the faster the solution is going to be. And then if you look at our technology, so FPGAs are common in computational storage. Look at our device itself. We have very high bandwidth. We go all the way up to 400 gigabits per second. But one of the things that I mentioned, and this is something that we highlight, is our two-dimensional NOC, network on chip. So we move data at over 20 terabits per second. And we connect it directly to our Ethernet, directly to PCI Express Gen 5, and connect that directly to our GDDR6, low cost, very high speed memory interface. And all of that gets connected to the FPGA fabric and to any other hard blocks we have inside our device, including our machine learning processors. So if you're doing data analytics, if you're doing compression, if you're doing these different use cases and workloads in the computational storage, it's reduce the number of times you're going to move over a network, move over a host interface, move over a memory interface. But also, once you get inside the device that's doing this work, it needs to move fast. And this is where we differentiate ourselves against our nearest competitors. This two-dimensional NOC is the fastest network on chip in the industry. And again, it's all done in hard logic. So saves all of the LUTs or the programmable logic for your application use cases.
Yeah, I think if you look at the size of data sets in general for a problem, whether or not how many are at petabyte scale, they certainly are increasing, right? And I think we see that across the board, you know, whether it's, you know, autonomous driving or e-retail or almost anything out there, the amount of data that people want to look at is increasing. So that's definitely an important point.
Another area to look at is Industry 4.0. That's where a lot of the IoT devices are coming from. And there are a lot of use cases. Yeah, a lot of use cases there that are real time. They can afford latency.
Absolutely true. With that, let's go to the second audience survey question. That question is, what experience does your organization have with computational storage? You can check all that apply. I'll launch this question. You should see the box pop up. Go ahead and just check the one. We'll give you a couple minutes to fill it out. And with that, let's go to the third panel question. That third panel question is, one of the stumbling blocks in getting data center traction for computational storage has been the perceived need to modify, port, or adapt applications. I know we talked a little bit about this in some of the presentations, but how big of an issue do you guys really think this is? And I guess more importantly, are there some examples of how companies have successfully tackled this and turned computational storage as a means to accelerate their application? Let's start with JB. I know you had a few listed out. We'll let you talk about those, and we'll go to Tom and Tony.
Okay. Yeah, I mean, this is a very interesting question because this is definitely one of the stumbling blocks. And the answer really has been, it depends. And I think Tom just kind of highlighted that. But we've got, some applications or some functions that are going to require no modification or no integration to take advantage of. And that's kind of where we've focused initially with the transparent compression function. No application integration required to take advantage of it. Plug in the drive. It's the functions are happening automatically. You don't have to trigger them, right? So that's one way to address it. I think another critical factor in overcoming this issue is going to be the standardization that Mike, you mentioned early in the meeting here about SNIA and NVMe org working on standards for how to access, configure, trigger, and utilize computational storage. So as those standards come out, now you don't have to worry as an adopter that you are really tied to one specific vendor, right? How the vendor goes about doing it on the back end may be different, but how you're going to access it and leverage those functions is going to be the same across vendors. So you do that integration once or modifications once and can use multiple vendors' products. Another way of overcoming this is how ScaleFlux has done some of this, and it sounds like PlyOps is there as well. Of we do the work to do the application integration and then offer it out to the community or offer it as again sort of a transparent functionality. ScaleFlux has done some of that with storage engines for MySQL and to take advantage of sparse data and take advantage of that transparent compression functionality. And then lastly, one problem that is a little stickier to overcome is making in a proprietary application, getting the application developer to see an economic advantage for themselves, right? I mean, if you've got your application and then there's only one vendor that offers a function, a computational storage function, it's not necessarily in your best interest to spend the effort to do those modifications to your application to work with one vendor's products. As the standards come out, then that helps alleviate that problem. Or as we ran into, or we experienced in our collaboration with Alibaba, if that vendor has a big enough, they're utilizing it and they're going to see the benefit internally, then there's incentive for them to move and make those changes. So as this was a published paper, this is public information, that Ali and ScaleFlux worked together on their PolarDB to do some computational storage functions, and that resulted in massive data movement reduction, significant boost in the transactions per second and queries per second in this hybrid transactional analytical processing database. So it was a very significant improvement in their TCO. So that's a real life example.
No, I think that's a great point. One thing I just want to throw in here too is I think there's a lot of problems that computational storage can also solve that aren't necessarily application level. Some things you talked about like compression and cryptography sort of issues and encryption, things like that. So most definitely. Tom, what do you think?
Sorry, take off my mute. So I can take you through a path. We've been down this path with several customers now, and you talk about the need to modify, port, and adapt applications. And of course, as an FPGA vendor, that's what our technology does. We allow the adaptability, but that isn't always the right solution when the cost and power are not aligned with, say, high volume use cases. And so we offer, and this is actual use cases or actual situations that we've been through where someone takes our data accelerator card, they use it for proof of concept, they build their application, then they move to an optimized PCB with our FPGA on board. But as the application evolves and as they move to higher volume, maybe because of market adoption, maybe because it's the particular use case, like autonomous vehicles is a great example, then you can take the technology and you'll harden the pieces of logic in an ASIC that you know aren't going to change. But for the things that might change, so it could be some standard, it could be because of the workloads, it could be because of giving flexibility to the ASIC in case there are issues with the ASIC. You can take FPGA IP and embed it in an ASIC. And what this does, it gives a path to end users to always have the flexibility, but only the amount of flexibility that you need in a particular use case. And so that's one of the ways that we help the market move into these new spaces, is use the FPGA for the application period. And when it turns into a voluminous or cost sensitive situation, you can move the IP into an ASIC development. That's how we address that situation in the market.
I like that. Tony, how about yourself? What do you guys at PlyOps think on this one?
Actually, this is a major pillar for us. And by the way, we are all for standardizations and committees and all of that. But as you guys know, these things take time. You know, in particular, we like if we can get key value interface over NVMe moved forward, or even key value over a network, those things are good things, but we can't wait for that. And as a matter of fact, when we go to customers, we don't say, hey, let's put a computational device in your network or in your infrastructure. What we say is, how can you run your application server faster and with more economical benefits? How can you create disaggregated storage with all of the problems that disaggregated storage and compute solves with isolation, etc. And you can do that at lower cost, create an infrastructure that works everywhere. So this is really, our goal is to make this as a non-issue. And really for block-based applications like relational databases, our device will be another Linux block device, just like an SSD would be, with the difference that we will transparently, and the keyword is transparently. We're not expecting the customer to make any changes to any software. To accelerate, protect, and help expand the capacity, add reliability to an array of SSDs adjacent to us. And same goes for NoSQL and analytics applications that use more of a modern key value type algorithm. Again, RKV API is just a binary compatible with these applications. It just sits there and works seamlessly. Examples of this includes Redis and many RocksDB-like solutions out there. So we really don't want to even bother the customer with trying to suggest that they have to change anything.
That's always the easiest sell, probably, isn't it?
Right.
Well, with that, we don't have any open questions. Again, this webinar is being recorded, and we'll provide a link of the recording to everybody who registered, along with a PDF of the slide set. Thank you again, JB, Tom, and Tony, for being sponsors for this webinar and for your views on this subject. I think we had a great discussion. Again, I'm Mike Human. Thank you for coming to the G2M Research webinar on computational storage, and have a great day.